It's great to be here and see all these old friends. I'm Adam Kalai. I'm at OpenAI, and I work on the safety systems team, work on safe and ethical computing.
Excuse me.
And I'm on Project CETI. Oh, sure. Thank you. And I'm going to tell you about a project today with David and Or, who are both here. And should be shocked. You too, but she backed out. Okay, and there's a quote, or there's variations on this quote, but this is by one of the co-founders of OpenAI that says, evals are surprisingly often all you need. So if you want to solve a problem, if you can evaluate the problem, it can make a lot of progress towards solving the problem. For kind of obvious reasons, but let me go through that. So if you just keep evaluating, if you want to evaluate translators, if you could evaluate a translator, you get one translator and you tweak it a little bit, you get another one, you check it, see if it's better, and you keep improving your translator, right? So if you can evaluate something, maybe you can make it better. Also, you want to just be able to validate that your translator is working for a scientific point of view. And are we translating stuff, or are we just getting hallucinations out of this translator? And moreover, if you can evaluate translators, you can maybe optimize, but if you can't evaluate your translators, you're kind of out of luck. I mean, how will you know if anything's good? So that's why evaluation is so important, which is why I think David was really pushing, let's work on this. Okay, so I'm going to talk about two things. The first thing is translation just from the output of the translator, which sounds impossible, but I'm going to try to convince you that maybe it is possible. So the first thing is, not with grounding, not with video and audio and everything. Just you have some translator. You take its output. Let's say it's in English, or it could be any language. Let's just say English, and you just want to look at that English and say, is this translator working? Right? Sounds impossible. So we have no reference. That's the challenge with these whale translations. We have or any animal. We have no ground truth translations. We have nobody no mermaid that speaks both languages. And so this would be great if possible, because hey, we don't have to, interact with the whales and annoy them. We didn't have to stick anything on them. We just listen to them with maybe a microphone in the water. Of course, it's very hard. How do we know the translator is not hallucinating and just making stuff up, as the language models tend to do? That's one thing I work on a lot at OpenAI, and I apologize for all the hallucination. Another thing is it'd be great if possible, because if you could just translate from the output of a translator, you could use this for any translation system. You could use it for translating Hebrew to any low-resource language, any language. You could try to translate music to English. You could translate anything to anything, and then you just look at the output and see if it's working. And the good thing is now we can test. What we're going to do in this, the first part of this talk, is we're going to test the methodology. So we can do it in a language where we do have some ground truth translations and see if this system is working as an evaluation. Okay. So we'll do it on some low-resource human languages, and we'll do it on some constructed languages, fake languages that people have made up and the AI has made up. And I think we'll have talks on that tomorrow. Is that right, as well? So it's kind of relevant. And then in part 2 of the talk, I'll talk about what if you do want to use interaction, what if you do want to use grounding and stuff like that. And that'll be more a theoretical analysis, and say, well, when will that help us out? All right, so this kind of quality evaluation is called reference-free, because you don't have any reference translations. You don't have any ground truth translations. But the goal is to get a translator from some source, could be anything, who knows, to target English. And now the obvious thing to do, and people do this, this is called machine translation with quality estimation. And they just ask a language model, how good is this translation? And that helps you to look at like fluency, like how good is it, the quality of the English in the writing. It might not be right, but okay. And you can, so we did some experiments where we took like a bunch of text from some low resource languages, and then we translated them and asked the language model, how good do they look? And we got a bunch of numbers, but how do you know if they're any good, right? So let's take an example. Here is some text in some script. I bet nobody here knows.
You translate using AI, and you
Yes.
evaluated.
Yes, you're right. We did use a language model to translate. We could have used anything in principle, but we used AI to translate. So we took a Wikipedia page. Does anyone know what language this is? Probably not, right? Some of these are pretty darn low resource languages like that. ChatGPT even doesn't really, it'll recognize the language, but depending on the model, it might not be able to translate very well. So we take this, we throw it into the translator, we get an output, we ask the language model, how good does this output look? So, okay, this is what the web page should be translated. It's some web page about trains. Okay, so GPT-4o gives you some translation, which isn't terrible, actually. It says something, something train, which I think is kind of right, will run on a special schedule for 11 days and blah, blah, blah. And its score is a 70, which is okay for the machine translation quality evaluation, because the English isn't really like great. It says, key points, bond, express train schedule. It's just the writing isn't great, but that's because it's like translating a language it doesn't know that well. Then you do GPT 3.5, which is like a really old version of GPT, and it gives you a lockdown, like COVID translation, which is very fluent. It's very clear. The government has decided to extend the lockdown for another 15 days in order to control the spread of COVID-19. The decision was taken after. It's like has nothing to do with the source. It's not some intent to deceive you. It's just. In my opinion, the reason these language models hallucinate, as an aside, is that we train them to be really good test takers. And when you take a test and somebody asks you a question, you could leave it blank or you could say, I don't know, but you'll get 0 points. So your better strategy is to, like students do, is like make their best guess. If somebody asks you, what's my birthday, you say, I don't know. If you're taking a test and somebody asks you, what's my birthday, you'll say September 7th. Why not? Like you have a 1 in 3, 6. Anyway, that's why I think language models hallucinate. It's another story, but they do hallucinate. They make stuff up. And so if you just follow this kind of naive plan, you'll end up scoring this evaluation, which is a pure fabrication, as higher than the other one. Makes sense. Of course, it's going to be impossible to evaluate a translation without the source. Okay, so here's another web page from, this one is from, the last one was from Santali. This is from Dzongkha. I don't know what language that is. GPT-4o gives something okay. GPT 3.5 says, I'm sorry, but I cannot fulfill that request. Gets a perfect score. Fluent English. Maybe that's what the web page says. Who knows? The source web page, right? So this is, I'm just pointing out this is not a great way to evaluate your language model. So that's why it seems impossible. Okay. But the trick is an evaluation we call ET. It's not exactly a normal acronym. We take the last letter of shuffle and the first letter of target. So we're going to shuffle the target. We're going to take the source, and what we're going to do is we're going to break it into segments, and we're going to translate each of those segments separately. Anyway, a lot of translation systems do that, not all of them. Some of them, they break it into paragraphs or sentences and translate each sentence separately. You might not get the perfect translation that way, but that's what we do. And then what we're going to do is we're going to take these two translations and we're going to take two copies of it. We're going to shuffle one of them around. So one of them we'll keep in order. Well, the other one we'll shuffle, and we'll give it to a language model, and we'll say which ordering is more plausible. Here's two translations. One's in order and one's scrambled. Which one makes more sense? And then we'll see if that works. Okay. And then okay. So and then hopefully if it's a good translation system, it should choose the one where the translation order is preserved. And we do this for many permutations, many times. So back to this example of the failure, when we take this same web page and we take two translations of GPT 3.5 and shuffle them, like half the sentences of GPT 3.5 are, I'm sorry, I can't fulfill that request. So a shuffled version, these actually look very similar. Don't read it, but I mean, it preserved the third slot, stayed the same, so it didn't really matter, and then the other two shuffled. So there's no really way to figure out what's going on from the GPT 3.5. You have a 50-50 chance of winning this game. But GPT 4o, I mean, the first paragraph starts with introduction. So that's a big hint, It starts with introduction. Maybe that should come first. And then it almost sounds like cheating. But hey, if you're trying to learn to translate, maybe learning to translate the word introduction is a good idea, because that will help you put things in order. And then that's the first thing you learn. And it's essentially like, you can think of it as a puzzle. We would like to give ChatGPT all the things shuffled at random and have it try to put them in the right order and see the chance it gets that right. And we're doing something very similar here. We're just showing it one correct and one shuffled, and seeing how often it gets it right. Okay, so the evaluation basically it takes, you segment the source, and I'll talk about how we'll do that, how we'll split it into segments. And then we'll translate each one separately, and we'll look at the probability that some shuffled version the probability that the correct order is more plausible than some random shuffled version. And we can do this. Not the same one. So we have one fixed language model for evaluating. You could use humans. There's nothing stopping you from using humans as judges here. Actually, we didn't do an experiment, but I'm quite sure the language model is way better at this game. What? Yeah, so there's a fixed language model we always use for this, which is GPT-03, but it's a reasoning language model, really good. And that language model, but I think you can think of, you should try to think of that as like a substitute for humans who look at this and say, does this make sense in the order it's coming? And then the things that are translating happen to be language models, but they could be any translation system you want. And but the key is that they're translating everything segment by segment. And then you ask the language model, which is more plausible, the unshuffled or the shuffled version, and you average over permutations and over many sources, and that gives you your score. Score of 100%, 1 means it's really good. A score of 0 means or 0.5 would really be the worst because you have no idea. You could be worse than 50%. So if you want to optimize, if you could sort of optimize for F, then it would be really good. It would be able to like put things in order and solve this puzzle of what's the right order of these pieces. And feel free to interrupt in the middle with questions. There.
But isn't it much easier to just learn to sort a language or to understand its order than to actually translate it?
Well, right, but we have an easy job in this talk. We're just evaluating. So we aren't translating. That's much harder. They have to somebody here, us, later, whatever, once we have all the data, will learn to translate. But the question for this talk is, can we evaluate a translator?
Yes, what I'm asking is, it could be that winning at this game is much easier. I
right.
know that the sound of a whale starts with going up from 0 noise and ends with going down from noise.
Good.
But I have no idea what it says. I can just order it correctly. So my translation would just be 1, 2, 3 according to the...
Right, but when you're translating each chunk, so you hear the sound of a whale, you have to decide what would you So, okay, there's something maybe you're saying which I like and I'm worried about. So let me give an example.
I think of, let's say, I have a single poem I know in English.
Right.
And now I know how to look at a whale sound. I have no idea what it says, but I know what is the first part, what is the middle part, what is the last part.
And so what do you translate them to in English? You say this is the beginning, hello, and then the second one. Exactly. Good. So so that's a very good point. And that's possible. And so another version of that would be like if you just had line numbers. If you have any text with line numbers and you decide to translate it, you could keep the line numbers and then, put whatever you want after that. It doesn't matter. Okay, so yes. So that's a failure mode of this evaluation. The good news is we'll see it because you look at the English and all it will say is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And every translation will be the same and it will just be these numbers. And so...
Unless, again, I'm hiding it with... Again, I have a list of poems in English, and instead of writing one, I will write the first line of a poem instead of the second.
But then it's sort of interchangeable. It is a possible failure mode. And maybe it's a good question if we can find a way to avoid that. But I do think that unless you have some sort of adversarial thing like you're describing, I think it might be pretty obvious from the translation if you see a bunch of line numbers or things like that, that's what's going on. But it's a good point. This is not a perfect evaluation.
Yeah, so I guess if you had a completely content-free translator, so it's just producing some random English text, you would expect this to collapse to 50%.
Right. Exactly. Yeah. Yeah, that's a good. It's a very good point, and I think it's a question of whether there's something that most languages, let's say human languages, don't have that property. Most programming languages don't have that property that you can tell just by listening where you are in a conversation. But there are very occasional things where you have line numbers or something like that, which does give it away. So it's interesting whether that would come up. And we do experiments to see whether that's coming up.
It's a good question because I think what you are saying is extremely right about written English or about written language, but when you listen to a person speak, then usually even if I know nothing about the language, I can tell when a sentence starts, when a sentence ends, when someone is starting to talk, when he finishes talking.
I disagree. I think there's exactly these different dialects of right, there's the Valley Girl accent, which, sorry, I don't know the technical term, but it ends in a way that always, I forget what it is, it sounds like a question or it doesn't sound, so that's, I think if it's in a language you speak or yeah, there's people in the room much more qualified to talk about this.
Yeah,
but I don't know if that's true.
It's not a single sentence beginning and end. You take a corpus. It's not.
We're chunking a conversation into segments,
Yeah.
and then the question is, can you tell from just listening to this segment? Can somebody, listening for me talk right now at this point in my talk, tell whether I'm at the beginning of the talk or the end of the talk or the middle of the talk? It's a bit hard in this case, but maybe for whales it's not. And we haven't seen that yet. So we'll see, maybe we will see a little bit of that. Okay. So first of all, one question is, how do you segment the text in the first place? So we did some experiments, which was fun. I know we're the theory team. But we did the experiments with Wikipedia, so that we just chunked the text based on 200 characters. Not very interesting. We did these alien languages, and we broke it by sentence. These alien languages all had sentences. We also have some simulations that I won't talk about on fake animal languages. And there, if you have animals talking, what you can do if they're turn-based animals is you can just chunk it based on the turn, translate what each animal is saying one by one, if it's turn-based. Okay, those are some things. And so one of the fun things, let me see, how did I get that far? Okay, here we go. So so we could segment based on the animals. Okay, so let's look at the experiments with aliens, because those are more fun.
Aren't you looking, depending on the chunking, at different processes? For example, this is done in neuroscience experiments a lot. Like I can shuffle the words within a sentence, I can shuffle the paragraphs, 100%. I can shuffle the pages, and I'm actually probing different levels, which is the semantic level, the actual grammar, and the micro level, or the cognitive structure.
Yeah,
and so on.
So I'm definitely thinking of the chunks as being big enough that they have substantial meaning. Because you get a pretty poor translation if you just chunk by word. So these should be paragraphs or sentences or something about.
But even if there is also the other extreme, right? If they're very large, it's saying
the
stories about a brother killing each other.
It'd be super interesting to do this experiment at different levels, because you could just take 4 whole conversations, right, from and try to put them in order, and I don't know if that would change things. It'd be interesting to do that. These are the chunks that we did in these experiments. So, so we started with a conlang, which is a constructed language. And there are people who work for decades constructing languages, so...
Tomorrow we'll have a talk about it.
Yes, and so this one is by Sylvia Sotomayor, who gave us permission to use her language in these experiments. And it's a language called Kellen, and it's spoken by the Kelleni, a humanoid species of the planet Turjamar. And she created this language because it does. One of the features is special is it doesn't have verbs, and I think most human languages have verbs. Yeah. Okay. So it's pretty cool and interesting to try to translate. So of course the whale languages might be much more different, but it's good to have some differences to see what's going on. And boy, these are all the web pages she's created. Each of these links is a web page about some aspect of the grammar. And so there's a lot of material here. And then there's a whole dictionary with thousands of words. And great for us, there's actually some text with ground truth. So she's created text in her language, and she gets to define what the ground truth translation is. And so we have text in her language in English. So let's use this language, because we're testing this methodology of, hey, how well can we evaluate a translation from its English or its target language only? So we can test it with this crazy language that she has. And so we can even test, this is a little confusing, we can test her ground truth translations to see how good they are, because we're not using ground. So we can look at what she wrote in English and see if it start with that. Let's take her ground truth translations. So let's take her text, and here's some story. And let's see if we permute these in English, if we'll be able to distinguish the correct order from the shuffled order. And so when you do that and you take the correct one of these is the correct one. Can anyone guess? I don't even know. Can you read it? Which one? The left one, yeah, great. It's not that hard to figure out. Okay, so what we do is we take basically something in her language, we break it up into chunks. Okay, we take one of those segments, and then we take all this text that defines her language, right? And then we throw it into...
That's all source.
That's all source.
That's all source.
Yeah. No, it's in English. It's describing...
sorry.
It's describing her language, the dictionary. It's got the grammar rules, everything. Okay. What I'm explaining right now, for a second, is how do we translate?
Yeah.
How are we going to build any translator for this thing? We need some translator. We could ask her. We could ask students to do it. I suppose it'd be just fine. But we could have students. Yeah, it'd be an interesting experience. Have students translate using her material, and then we could grade the students on how good they are. But anyway, we throw it into a language model, and it's kind of amazing to me that this works at all. We throw it into some. The amount of text is so large that it only fits in these newer language models that are designed to have like a million token context. Anyway, so we throw it into some of these language models, and it outputs some translation of some sentence, and then we do this for each sentence in turn, and then we run this experiment. And okay, so is the setup clear? Okay. Now you're also worried that her script is on the web. Maybe the language model already knows it. Maybe it already knows all the translations. So we said, let's just make some more constructed languages that don't exist on the web. So we'll get the language model to generate, it took her decades, but we asked the language model, can you make up a fake script? And in minutes or shorter, it generates like, a grammar, a lexicon, source and translated things, similar to, probably not as good, but it's impressive, much better than I would do. And so, and these languages have very cool properties. Like there's one that the one that translates the worst has this property: the Inrithan have a unique sensory organ that allows them to perceive the passage of time as a spatial dimension. They see time similarly to how humans perceive color, allowing them to navigate potential future events and make decisions by viewing time as a landscape of possibility. So you can imagine if some alien has this ability, then it's going to be hard to translate their language. That's why maybe that one is hard. Each of the aliens has their own special property, and then there are just pages and pages of definitions of their language, and it's very creative. And
you constructed languages according to this specification, and you've got web pages described.
Yes, exactly.
Doing all this.
Yes. I mean, I didn't do it, but the language model did it, yeah. Just from some very simple description. There's a few steps. I simplified it, but basically there's a few steps where you ask it to construct a language, construct a grammar, make some dictionary, make some translations back and forth, and it does all of that. Okay. Yeah. So that the conlang people might be out of a job soon too, which would be a shame. No, it's not a job. Their languages are probably better. So then we can take, the good thing about all these languages is that we have ground truth. So we have some translations in English and their source, according to the authors. Kellen is a real one. I hope to have some more real ones here. We have the speakers tomorrow. We could try to translate some of their languages. And then we have 10 others. And so for each of those languages, we take our 10 sources. We have 10 sources for each one. At least Kellen has like 18, I think. And then we shuffle each one several times and score it. And so this shuffle target ET evaluation is on the y-axis. So bigger is better. And then on the x-axis is we can use just some standard machine translation evaluation that uses the ground truth translations to evaluate how good is it. We're going to look at the translation in English, look at the author's actual translation, figure out how similar they are. That's a very standard problem in machine learning. And this one is called Gemba, the evaluation. And so, okay, and so then we can plot how correlated they are, and they're very correlated with a 0.63. Each dot here is one of the languages, and then one model. So it could be the translator that's GPT 4.1, 4.1 mini, or 4.1 nano. We could do more if we want. And then there's also the ground truth. Now the ground truth, according to the Gemba evaluation, Gemba is looking at, literally at the ground truth on the left and the same thing on the right. And so it always scores basically 100%. So that makes sense. Now our eval is more complicated. When it's evaluating the ground truth, it doesn't have the ground truth. So it's taking the ground truth and some permutation of the ground truth and trying to put it in the right order, basically. And so usually it does really well, and it gets a score very, very close to 1. But that language was the one I mentioned that has like the passage of time in a weird way, where it's not even doing great at translating that. So yeah, so the ground truth is failing there. Okay, so that's the ground truth, and then we have 3 models, and as you would expect, the bigger model, GPT 4.1, tends to do better, both in terms of R score and in terms of Gemba, or in terms of this standard machine learning thing. And then the medium model, mini, does worse, somewhere a little worse, and then the nano does even worse typically. But not always. Sometimes one. But the good thing is this evaluation is correlated, so that gives us some confidence that this might be a reasonable way to.
The way that you judge the quality of the translation is with this order of business?
Yeah. That's the y-axis, is like how good is this, how much, when we look at the English, how well are we able to put it in order? And that's the y-axis. The x-axis is, since we happen to have on these languages ground truth, we can actually tell how good a translation it is. And so we're seeing, like, does this shuffling evaluation, is this a good way to evaluate languages? For these crazy alien languages, it is. Now, the good thing is these alien languages have some weird properties. So we expect animal languages to be quite different than human languages. So alien languages, the fact that they're different from human languages is good. We also have some experiments with constructed animal languages that are similar, where you have, fake animals talking to each other. I'm not showing those results because you'll probably look, if somebody looked at the details, you'd be like, oh, that's not biologically plausible. But it gives similar results. Okay, and then there's another standard evaluation called BLEURT, B-L-E-U-R-T, and it's also correlated under that. So these same thing with just a different metric for human quality. This is like an older one, but it's a very standard one. Okay, so what are some of the animal failure modes? So first of all, like, why is this eval, back to your question, why is this eval maybe not right? So first of all, this whole thing may not work. Some people say, I don't believe it, if you can't translate at all animal communication. If there's just no way to express in English what the animals are saying, we're out of luck, of course. But I think many of us here think there's some way to describe in English what it is they're talking about. One other problem is specific to this, is that maybe you can translate whole conversations or something, but you can't translate a chunk. Whatever our segments are. Maybe our segments are too small or something like that, and then you can't meaningfully translate based on a segment. You really need to see the whole conversation. And that happens. It's useful. I find it useful to think of analogies to programming or other languages, at least for me, that I know. Like, if you want to translate from one programming language to another, it's not always possible to do it at a line-by-line level. I mean, somebody reading it still might be able to understand it and put them in order, but the way that the languages are structured is pretty different. So sometimes translating on a chunk-by-chunk, segment-by-segment level might be hard. In human language, that often works fine. And then there's two problems with the eval in terms of it can be pessimistic, meaning that we saw in one case the ground truth translator was not super perfect. It didn't get a perfect score. So if your language, if these were cows and all they said was, I'm happy, I'm sad, right? You wouldn't be able to put those, if they all just repeated the same word moo, and that's all they said with a happy moo all the time, and everyone was, a good day, or maybe it's like it's sunny, and all they did for like an hour was all say, hey, it's sunny. It's literally the same thing. There's no ordering. And then the next day they're all saying, oh, it's rainy. And there'd be so this permutation trick wouldn't work at all. So that's one failure mode. And you might have a great translator that translates it's sunny to the right cow sound and it's rainy to the right cow sound, but you'd have no hope of translating. The other way is what you were referring to, that it could be optimistic. So you could have a bad translator that's kind of tricking the system in the same way that the hallucinations were. And that was my line numbers example. Or as you were saying, maybe if the conversation always started in a low sound and then built to a high sound and then we always finish in the middle, maybe you could figure out the order of chunks just from the sound. Also, there could be ambiguities which are kind of hard to piece apart from just listening. Maybe you can't distinguish when a whale is saying, I'm hungry, from let's dive. Because maybe, practically speaking, they always do the same thing after it, I'm hungry, and then they dive. So is there even a semantic? There might be a difference. And, so to do something like that, you could run an experiment where you keep whales in captivity, don't feed them, and then see if they say the thing, which would mean I'm hungry because they don't plan to dive. Or so, there might be some intervention you could do, which we don't want to do. That's really torturous, that one I described. But there are failure modes of this eval where they're just things which are hard to distinguish as symmetries or certain things in the language which we can't distinguish. But those aren't necessarily the worst problems to have. Okay, so any more questions on this first part of the ET shuffling word evaluation?
A question about the plot you showed before, the correlation between your ET and this common translation metrics. I was wondering if you did some analysis also changing the split, like the size of the chunks. And how the correlation evolves.
Yes.
And yeah, I'm also thinking maybe in some languages you repeat stuff a lot. Right. So if you hit the wrong periodicity, it's very hard to reconstruct the order.
Right. No, that's a great suggestion, and it's related to what he was saying before about the chunk size. Yeah, I think that's a great experiment to do, and we haven't done it. But that would be really interesting. Yeah. You're right that obviously in some limit case it would fail if we made the chunk down to one letter, one bit, and then and I don't know what would happen if we made the chunk super large. And yeah, it's a really good question how it varies with chunk size.
I was thinking that maybe especially in audio communication, often you repeat a lot, and when you repeat a lot, then the order doesn't matter, no? If they are different chunks.
Yeah, it's going to be very hard to piece it together perfectly. But you can still piece it together somewhat, right? Think of this jigsaw puzzle, right? And you have essentially pieces, and we're trying to put them, you're taking this English, that translation that we think the whale said, but then we just permute it around, and now you're trying to put it together, and you say, okay, well, these three pieces where the whale's saying all of the same thing, they kind of go together. So it'll get a higher score, but not a perfect score, because it'll be able to put essentially these three pieces. We know they're together. We don't know which order they belong in, and same for down. Does that make sense? So we'll do better. So it might do okay at ranking, but we won't get a perfect score in terms of being able to fully piece together a conversation in exactly the right order, which we wouldn't be able to do in English on a very long conversation either.
I see. Okay. And I have a second comment. Here, as a final measure, you ask directly to the language model, no? How good is this translation? While in an older works of yours, you look at the text probabilities.
Right. We could do the text. Okay. So we could look at. We're not asking how good. We're asking which version is better, the correct order. But we could look at what you're getting at, which is the language model assigns probabilities to any string. And we could look at whether the probability of this English string is higher than the probability of another English string. And that's a good idea as well. We didn't try that. A question behind you. Thank you.
Yeah, it was just, I guess, thinking about the applications to animal communication, and in my mind, having a good generative model probably precedes translation in a lot of scenarios, and so I was just curious if you had applied these evaluation criteria to actually train generative models of English. So, as something, distinct from, say, the GPT rules for training a generative model. You could apply these same criteria to create generative models of English and to see what does it generate.
Did you want to say something about that, or?
How BERT is trained.
Yeah.
I guess there's particular chunking and kind of particular settings for the choices you've made here in the evaluation that you could apply to score and guide the development of a self-supervised generative model of text.
But it is true that if you want to make a generative model of English, like Or was saying, that's one of the tricks they use is sometimes shuffling things, and it is you would want your language, your model of English, to have this property that the pieces make more sense in order than they do out of order. Yeah. Any other questions? Okay.
Yeah, if you could go back to the slide on the failure modes really quick, because I feel like a lot of this is kind of muddying the waters of when do we actually know, like, correlation versus causation, right? And these failure modes, how are these potentially detected in practice? Like, when do you know, do you have checks for being able to evaluate whether or not your evaluation is in one of these failure modes, or are you kind of having to base it off of conjecture?
Yeah, so that's a great question. So there are some, so that's really, that will be a good segue to the second part, which is, what if we do want to use grounding? I mean, ultimately, you do get a better causation evaluation if you're using grounding. Like if you're looking at what the whales are actually doing in the water or the animals are doing. And so there's 3 levels. You can just listen. That was the first part of the talk, and we're trying to do the best we can. And I think the experiments are promising. I would say that maybe you can kind of evaluate how good translators are from listening. I tend to think of this thing as more tending to be more pessimistic than optimistic. So I think sometimes you'll get good translations, and this thing won't be able to tell that they're good translations because it won't be able to put them in the right order more often than the reverse, where you'll have really random, totally wrong translations, but for some reason the language model can figure out the order. At least I haven't seen evidence of that in any of the experiments. There's 3 levels, right? You've got just listening, then you've got listening and watching, or like kind of getting data from the whales. That gives you extra confidence. And then, of course, you have interaction, playback, where you can really do the causation. And so I thought I'd just talk briefly about interaction in machine learning in general and how much it helps for learning and evaluation. If you're trying to learn a function, you've got some data, x, y, trying to learn some classifier to approximate some function, and you've got a bunch of examples. Normal learning, you don't do any interaction. In interactive learning, you get to maybe ask a question about an example. You get to find some example in some pool and ask for its label, and then somebody gives you that label, and then you get to say, okay, that's great, thank you. Now, how much extra would you be willing to pay for an example like that versus just getting more and more data cheap? And so let's say you're just trying to learn a binary feature. So your x's are a bunch of 0s and 1s, and your y is one of these columns, but you don't know which one. And so some feature, maybe one of the features is the person's sex or something else. I don't know, a bunch of binary features about people. Well, sex is not necessarily binary, but let's say it is, and so on. So okay, so what you have is let's do the alien example. You have some alien, it looks at a person, and it says some remark. Oops. So you have the alien look at the person, it says something, then it looks at another person, it says the same thing, then it looks at another person, and it says something different, and you're trying to learn and figure out what do these aliens' words mean, and let's say there's just 2 words for the alien, and you're trying to guess, what is it? Anyone have a guess of what these words mean? I don't know. All right. What'd you say?
Color of the shirt.
color of the shirt. It could be. So, you know, it seems to be, at least in this example, based on the number of features we had, very quickly you narrow it down, and it's the third column. That's the only attribute. Maybe it's sex of the person, maybe it's their shirt color. But usually, when you're learning something very simple like this, it's enough to just get random samples, and you don't benefit from creating, you know, from interacting and asking, except if there's two features which are really, really correlated, then you can piece that apart by asking a question. Like here, you can maybe, you know, construct an example or take somebody from the pool who, you know, maybe is it the shirt color, is it the gender, if people are always, or the sex, if they're always super correlated, and then you can answer that. So that's the, you know, when kind of common sense, but it's kind of obvious. Like, as long as your feature is distinctive, you don't really need interaction. But if two features are super correlated, you do. Well, that's what it is. Okay, and then you get an answer, and then you can figure out which feature it is. Okay, and there's a different story when you're trying to learn a real value, some threshold. Okay, so the alien looks at a person, they say natak, dolag, and you know, okay, and then they say dolag, and so maybe the difference in this case is, are they tall or short, right? And so we're trying to figure out what's their threshold for this concept of tall that they have. Here, there is something, you know, theoretically you can do, which is you can do binary search. You know, if you find a person who's halfway between this person and that person, you can keep asking, oh, what about this person? And you keep doing asking about people in the middle, and you can narrow down their threshold very quickly and figure out what do you think tall is? You know, is this person tall? And then I get somebody else, and I look around the audience and find somebody who's halfway between the two. You need a lot of people, but does that make sense? And then they get an answer, and you can learn the threshold. So for continuous features, we theoretical computer scientists and machine learning got very excited for a while that, hey, this gives you an exponential savings, and we get more and more digits of the threshold of tall or short. But, you know, I mean, from the SETI perspective, I think if we understood that they were commenting on the swimmers in the water and had some comment that one was big or bigger than another, we'd be thrilled if we understood their word. You know, that word means big. Wow, you know, do we really need to know the number of digits? Not really. So we have a model of this to try to understand, you know, when we expect to get a big savings for using interaction. And so we imagine you're translating from the source, which could be Walish or whatever, to some target human language, English. And then there's some observations, maybe the depth of the whale, maybe, you know, I know on the boat they're sometimes taking notes in English even, which is great because those can be very helpful for you know, helpful metadata to figure out what's going on. And then there's some loss. So that we have, first of all, we have some data, maybe some training data and test data. And that makes sense. We take our data, which is source, target, and metadata. And then we have some loss, which looks at the translation and says, how consistent is this translation with the metadata? The translation, you know, says the whales are saying like, oh, it's so annoying. These two swimmers are, you know, they keep coming at us. And then the person in the boat's writing in English, there's two swimmers in the water. And then you'd be like, this is amazing. You know, the translation and the metadata are so aligned. So you have some alignment score loss that scores how good or bad the translation and the observations are. And of course, we're going to try to minimize this loss, but we also want the translations to be plausible in English.
You didn't make the event, or did you?
No, so this is just observed. This is just observed. But you could make the event. You could plop in an extra swimmer and let's see how good they are at counting. Let's put in 17 swimmers and see. Right, but here we're just talking about observations for a second. And then we translate, and we can do it all at once or in chunks like we're doing before. And then we get some observation, and we look. And there's some prompt which says, you know, we want, time is short. Let me skip that. All right, so the main theoretical observation that we have here is about what they call scaling laws, about I've presented this before, so it's kind of interesting to see if I can do it. But basically, when you think about as you make your model bigger and bigger, how does your performance improve? You should get better performance with a bigger model if you can find the best big model. If you find a bad big model, that's not going to help. And that's, basically we call that a scaling law. As we make the models bigger and bigger, if we're doing a good job training them, what is their loss? And you expect it to go down. It won't go down to 0 because we're not going to perfectly translate and understand everything. But okay, so we'll have some loss. Remember, the loss is basically telling us how connected is the translation to the observations we have. It could also be a loss that captures this permutation stuff and other things. You could put in other things into the loss as well. And then we're going to have 2 models. One that we imagine that we train with interaction, and one that we train non-interactively just by listening. And so we'll get more data by just listening, right? Like if you just put a microphone in the water, you get a lot more data than if you have to have a conversation with a whale. Like a lot more data, right? I mean, think about it per dollar or per human hour or whatever. I mean, it's the human effort is really the way to think about it, but you can translate that to dollars, let's say. For the same amount of money or time, you would get 100 or 1,000 times more code. I don't know. It would be a lot more, right, from just listening than from having to have a conversation.
So when you have the blue and the yellow, it's for the same amount of money?
Yes.
Got it. Okay.
Exactly. Thank you.
The number of samples cost something, the same amount for interaction?
Yeah. So let's say you get like 1,000 times more samples with just listening than you do from interacting, which enables you to train a bigger model. But then there's a question of how much bigger. So the beauty of interacting is every bit you get could potentially be, it won't necessarily, but potentially be right. In the experiment where you ask about the height of somebody, the swimmer or whatever, if you really knew that's what you were doing, which you wouldn't, but and then you do some experiment and you throw this other swimmer in the water and it says, Natak, and you say, aha, so I know for sure that the threshold is above that, which is very optimistic. But so you get these small models, but they're very accurate. With the listening model, you'll train a much bigger model, but it won't be actually. The problem is the bigger model will actually have a loss that's higher than the best model of its size. So you fix 2 sizes. And so what I'm going to hold here is basically constant is the ratio of the size of the model you would get from listening to the size of a model you would get from interacting. And the listening model will be, I don't know, let's say 100 times bigger. Maybe you get 1,000 times more data or even more, but because of the imperfections in your model, you can't actually train as big ones. So with this fixed, the theory says that you need a certain size gap. You need this, the performance of the best model to be much better when you make the model 100 times bigger. So it kind of depends on where you are in the space. So think of it this way. Like if you had the very perfect model, so we've trained, let's say we had billions of dollars, which would be amazing, to train for Project CETI, right? And we've got this model, and it's like, really understood almost all of the whalish. And now we're down to, these finer details of, well, what does a whale think is a, T squid or a big whatever swimmer? And so then the interaction will really get us those last bits of accuracy because we can keep, showing it different swimmers of different sizes and get those digits, really get it perfect. That's when we're down here, and the gap between, a model and the next model 100 times bigger is not very big. So we're not benefiting. It's not big enough to merit listening, and actually we'll get more extra bits from interacting down here on the huge models. Possibly also on the very small models, the interaction will help. But I don't know. This is somewhat hand wavy, but the theory says that if the model, if you increase the model by 100 times, if you're in that part of the space where you get a big win from a much bigger model, which is often the case, then actually listening is more cost effective than interaction.
So regarding the interactive model, I'm just curious because there's no way to know really if they're responding to throwing another swimmer in. I mean, even in captive studies, Diana, you know more than I do about this. It's really hard to understand, for the animal to understand what you're asking of it, That's a huge issue. So I'm just curious how you're
Good. Thank you. I'm glad to hear that. So our model, we came with with an ethical stance that we were trying to show that listening is better. So we wanted to be conservative and give the playback experiment, the interactive one, the most benefit of the doubt. So in this model, we're like, you get perfect information. In our theoretical model, it's like, nope, I know that or maybe it's hard, but no, imagine if it was perfect. Each experiment you do, you knew exactly what the whale thought you were asking, and you got that. And then still, in many cases, listening is better. So in the case where the playback experiment is not working, and you're not getting any signal or even very little information about what it is it means that you're hearing from the whale, then even more.
Yeah, it has a lot of room for error.
Yeah, there's slack. Yeah, there's some slack in that analysis, But I think there might be some truth that, I think the truth is that from a statistical point of view, the amount of data, you usually get a much bigger win from collecting a lot more listening data than you do from interaction.
So you're kind of like a therapy type of explanation, to really listen.
Yeah.
Just following up what Denise is saying, I think there's also maybe saying listening and watching.
Yes.
Too, because that's a whole other thing, right? It's
Yes, in this part of the talk, they were using the grounding, like the metadata, the video, the text, all that stuff we just abstracted into this loss function.
Yeah.
But that can help a lot.
Because cost-wise, you could be observing and recording at the same time.
And that defines the loss, which wasn't even present in the first part of the talk. So that would just all be missed.
So the other thing that I think we could refine this model a bit is the amount of noise you have in the data, because you have other animals there, shrimp clicks, noise, boat noise, all sorts of other stuff, and in theory, right, supposing that other noise is less perplex, right? You're looking at this complicated vocalizations from the animals, and hopefully a lot of the other things in the environment are more easily modeled. And you can imagine that at some point, as you add more data, those other sources of acoustics will just be factored out. But in the beginning, right, it's going to dominate your model is this background acoustics.
Mm-hmm. Yeah, that's definitely makes a lot of sense. It's interesting to think about how that interacts with the question of whether you do playback or not. I don't have a clear picture. Yeah.
So one question and then two questions. So does that assume that you already have an alphabet of language?
This is a super abstract thing, so it's kind of just like, how big a model can I get from this? How you go about getting that model is abstracted away, so it hasn't been answered. So,
right, because that's one thing. When the observation is like the search space is so gigantic.
Right. I mean, yeah, exactly. And so there's a huge also computational question, which is maybe playback helps not because for data, but like if I'm trying to learn a language from you, because I know you speak many languages, and I hold this up, and we don't speak anything in common, and I hold this up, and you say in your language, what the word for this is. I've now learned what microphone is. It's helped me for a computational reason also, because now I just did a very clear playback experiment where, you see what I mean, where I got a word and I didn't have to piece it together from listening to hours of recordings of you talking and trying to guess what microphone is. So there's a whole computational aspect of it which I haven't gotten into. And this is all meant to be about evaluation and validation. Maybe I should conclude because I'm over time. But validation by listening may be possible. Training is a totally different story. I think that the metadata is going to be super useful for the training, or you need some amount of it. But for evaluation, maybe this shuffling thing in English is good enough. It seems to be good enough on these constructed languages to tell whether a translator is hokey and just hallucinating or whether it's actually got some signal. And then, obviously interaction may be helpful in certain cases. I think our theory is helpful for helping understand how much data you need to evaluate, but not necessarily to train models. So it's great that you're getting the data because we really need to train the models. And yeah, keep up the great work. I'm humbled to speak in front of all of you because you're all doing the hard work of understanding the animals, and we're just trying to do some theory. But thank you very much.
First, thanks, Adam, for that. And yeah, this was kind of, we also think this talk is kind of like several years in the future of like, say we're getting to the point where there's some kind of very sophisticated communication, we think we're translating correctly, how would we even know that our translation is working? So kind of, we're kind of jumping ahead several years to imagine we're at that place and think about how to validate it. But I don't want to jump too much into our coffee time, but go for it.
Can I suggest I would love to see the synthetic language experiment with noise added, and see how long it can survive with more and more increases in noise. Because when we're trying to tokenize what's coming in from the animals, right?
That's a good idea.
It is very noisy.
Yeah.
And so seeing if this still works, and what level of noise does it create a cliff, be extremely useful.
Thank you. Great. And I'm around. Thank you. Great question. And I'm around during the coffee break, so just keep asking questions, but maybe.
All right. Thanks. We'll take a 30-minute break, and then we'll do a talk on WAM. And so 30 minutes, and we'll see you back.
Not semantically. Not semantically.